Paris 10 euros. I have to be up to the task. So does it work? Maybe it's my fault. So,
you have to make sure this thing is pointed down as well.
I will plug. So you can't this time out.
Yes.
Because people know I tend to give long talks, so I will try to be brave and concise. But I mean the topic is difficult.
What we do is difficult.
Yeah, because I should start by thanking Samson again for his patience with me, because I remember when he hired me, I was doing rewriting theory, and I was like obsessed with it, and I would of course try to become a good semantician, but okay, well, it takes time, as you know, it's not an easy topic. And Samson was always very kind with me, and yes. But here, I want to say that since I left Edinburgh, you know, all these ideas I accumulated there kind of developed, okay? And for me, it was quite impressive to see the trajectory of Samson, you know, because I tend to be very fanatical about things. So rewriting, then game semantics, and then I see Samson going in some new, you know, like superposition of two academic lives, like dialogue games, the Samson I know and I love. And, well, all these Frobenius algebras. And so I'm sure this had an impact on me, and I thought, is there a way to connect them, okay? And clearly this was quite far, I mean, this is quite, but I started developing an intermediate place where maybe we could understand proofs as some kind of string diagrams like the one we've seen, okay? And this was where I was about 5 years ago, 5, 6 years ago. But more recently, and because of this event, I thought maybe I should really try to understand. You remember Jamie Vicari's talk, so where are we? What does it look like? It's quite, I mean, you know, we're used to know that the world is more intricate than we think. It's not so hard. And so I try to explain something, and we'll see, you know, this is my kind of position. I try, of course, I'm French, okay, I cannot escape from it, but I try to learn some things from the other side, okay? And it's clear in the case of semantics that, you know, there is these areas here which are very, you know, linear logic and so on, and here a completely different view. And what is so fascinating is to try to change mind, you know, it's like two hemispheres. And here, interestingly, the connection between, you know, the games and cobordism comes from...
Why Scotland blank? Why Scotland blank?
This is, you know, this is, I mean, England and France, at the time, Henry II, so it's quite... but it's... Anyway, so what is interesting is that in order to connect these things, one needs to use, you know, the Australian connection. And I think this is the Commonwealth, okay? But still, and there is something very like unifying in these places. Okay? So what I will try really is nothing but an attempt to understand a deep relationship between linear logic and star autonomous categories on the one hand, and cobordism, which was discovered by Ryan Day and Ross Street. And what I'm doing here is only adapting this thing they discovered to game semantics. Okay? So, because as we will see, my philosophy is that linear logic and so star autonomous categories are like degenerate game semantics, okay, in the algebraic sense, of course. So, and really the original purpose of my work is to have something like a connection, good understanding of proposition as types, so logic really, and your proposition as games and game semantics, and try to build something that would be very algebraic and neat, based on this idea that game semantics is a syntax, it could be called game syntax, of continuations, formulated in the language of string diagrams. So typically continuations, I think, many of you here know what they mean. So the idea is that you have a binary function on natural numbers, but you want to understand in which order it calls its arguments. And the beautiful idea developed here by Stretchy is that, there is, maybe we could take a double negation of natural numbers, so we replace every type by their double negations, and then it will be possible to separate the left to right implementation from the right to left implementation. So typically, this is the lambda term that would have been written at the time in the 70s for the left to right implementation of the addition, and this is the game semantic view of it. Okay, so question answer here. This is for the output, but clearly you see this is the left to right implementation of the addition, where the first question is asked on the left, and then the second question is asked on the right. Okay. And there is the other strategy, which just returns the orientation of things. And in order to understand this phenomena, and also the notion of polarity, which arose in the 90s, maybe more on the French side, I found useful to take linear logic again, but remove this axiom that every formula is equal to its double negation. Okay? And the idea is that, after all, logic is a very concrete thing. So if I negate it, it's like I give my turn to the opponent, and then if we negate again, it's my turn, and we should see it. Okay? We should not forget it. And this relaxation, my claim is that this is the essence of dialogue games. So what is this logic I obtained is, I didn't want to give it a name, but people asked me to give a name, so in the end I gave that name, but really the idea is that this is the primitive kernel of logic. Okay, so it's not a beautiful logic, on the contrary, it's the most common one. So it's like the bad weed of logic, Every time you want to have a garden, you will see this logic inside your logic. So you see it's very basic. You have a few hypotheses here and an output here, the conclusion, and then you build your proof exactly as you would do normally, but the only difference is instead of having implication, you have negation here. So these are the two rules for negation, and that's it. Okay, so nothing much. And the idea is that the logic one obtains is some kind of refinement of linear logic. So here, this is, if you like, this logic where we see the negations, and if we forget that we see the negations, we go down linear logic. And so the interesting, the purpose of this picture is to say it's an interesting organization, because whenever there is something interesting in linear logic, we may try to lift it to a situation where negation is not involuted. And of course, you start like this, and then you try to extend. And this is exactly what I'm doing here. I take a result about Frobenius algebras, and I will lift it to a situation where negation is not involutive. So we'll build some kind of non-involutive or lax notion of Frobenius algebra. So that's the purpose of the second part of the talk. And so typically, the left to right implementation of addition would be described by this derivation tree, whereas, and then this is the associated strategy, and this is the other derivation tree, and this is the associated strategy, and there is a perfect match between the proofs, if you like, formulated in this language, and the strategies here. This perfect match is really just a reformulation of the full definability rules obtained in game theory. The point is that now we have an algebraic formulation of this correspondence, and we'll see an application of that when I speak about Frobenius algebras. So we have this logic, so we should have a categorical account of it. So the categorical account is provided by dialog categories. So a dialog category is just, it's a very simple thing, it's a monoidal category with a left duality, so you can curvify on the left and on the right. Okay? And here I'm very serious about monoidal, I don't want it to be symmetric, okay? But I will add a little notion of cycle or wheel, okay? And so what this extra information enables you to do is when you have a proof of A tensor B into bottom, the false, then you can permute the order of hypothesis. And what you get is something I call helical, because it's a refinement of cyclic monoidal categories where you know how many times you turn. Okay? And then you should satisfy a coherence property which tells what? It says that if you have a proof with two inputs, and this is bottom here, if you turn like this, so this is the wheel, well, if you have three inputs and you turn one and then two inputs, it should be the same as turning the two first like this. So this is just a very natural hypothesis on the notion of cycle in proof theory. Okay? And it's possible to show that this formulation is equivalent to having an isomorphism between the left and the right negation satisfying this diagram. So it's a very basic notion, but the important thing is that it's in between, if you like, proof theory and not theory. So let me explain why. So if we build a free dialog category, so we really follow Lambec's philosophy that, well, let's build a free dialog category, then, well, what we find out is that, of course, the objects of the category are formulas, the morphisms are proofs, okay? But these proofs, in fact, are some things like ribbon diagrams, okay? So what does it mean? It means that among all the dialog categories, there is a very specific class of dialog category, which are, so ribbon categories, if you like, just like something like compact closed categories, but in the braided case. And negation is defined in the most brutal way. Okay, it's defined like this. Okay, no, it's not defined like this. Or in blue. Can you see? Okay, negation of that. I will try to find. No, this erases. And okay, negation. No, it's not.
If they're dead, put them in the bin.
Sorry.
If they're dead, put them in the bin. Then the next speaker will not have to try them again.
No, but it's okay. It's okay. I think it works like this. Right is okay. So you define it like this. So you fix a bottom element. So you fix a bottom element in your category, and then you define negation as this. So this is involutive negation tensor this bottom, this fixed bottom. And the point, and this is not so easy to prove, but the point is that this defines a dialog category. So this negation satisfies all the property of the logical negation. And the important fact, if you like, is that this functor, what it does, it takes a proof and it forgets it's a proof. It translates it into the tangle, the topological tangle of the flow of negation. It just cares about, if you like, what happens to the bottom. Okay? And this is really, I see it as some kind of essence of game semantics. You start from a logical category, and then you have a topological category, and what you do is you take a proof, and you translate it as a tangle, but the point is that what you forget here is all the logical structure. You only remember the flow of negations. Okay? If you do that, okay, so this is, but if you do that, and this is the difficult thing to prove, this is faithful. So which means that two proofs formulated in the sequent calculus, Anna-Gensen, are equal to the equational theory if and only if they have the same associated game semantics. But here it's a topological game semantic, if you wish. So I will, oh my god, how much time do we have? It's too much resource for me. So, yes, I can pick anyone. So, okay, so this is the idea, and really, okay, I think this thing is really a transnational thing. You need to be a bit English, Scottish, French, Australian. I mean, and really, you know, it's just trying to understand the connection between what we are doing and what people do in, you know, functorial, what they call functorial knot theory. Okay, so we interpret a proof as a tangle, and the functor is faithful. So an example of that is, okay, imagine this is a typical coherence theorem, if you like. So imagine that you have a diagram like this in a given dialog category. So it's, if you like, it's very logical in the sense that these are really implications, logical implications. And you wonder whether this diagram commutes. So you translate it as, you know, like derivation trees. And what the theorem tells is that in order to check whether the proofs are equal, you know, in the Gensen style, it's sufficient to follow the track of the force, if you like. So this is bottom here, so this is negation, if you like, here. And we track negation in the proof, and we go back. And, well, if we track it like this, and if we do it on the other proof, and we track also the flow of the atom here, we get the same tangles, thus the proofs are equal. And in a way, okay, you see, because it's very algebraic, it's a mix of game semantics, but also one can recognize the geometry of interaction here. But if you like, if you look at it from the point of view of game semantics, it's really like opponent plays here, something happens in the proof, and then the signal comes out. And here, opponent plays, something happens, and here we don't forget the way the signal is braided. That's it. Okay. So this is part one of the talk. It's, okay, game semantics can be seen, it's possible to, you know, so yes, like foundations. So it's possible to have a topological view of proofs. Okay. Then the question is, this is fine, okay? So in particular, what is interesting in this kind of theorem is that, for instance, a typical braided dialog category like this is take a quantum group, so Hopf algebra with the good structure, the category of modules, but not just finite dimensional, all dimensions, they have a negation which is not involutive, and thus, if you like, if you look at the kind of canonical structure, categorical structure of infinite dimensional modules, you will get strategies. Okay? So you will get innocent strategies between them, but seen as tangled. Okay, so that's pleasant. At the same time, the question is, can we carry on, and in particular have, you know, kind of even more geometric view of them. I mean, of these flows here. Can we understand them in other ways? And that's where Frobenius comes in. But in order to prepare a bit the Frobenius view, we should try to understand, I mean, one needs to understand what are the kind of internal structure of a dialog category. So a very important thing about dialog categories is that, and it's a famous fact about negation, that negation is adjoint to itself, because the proof from A to not B is a proof from B to not A, thus it's a map from not A to B, it's here. And here, okay, this is really fundamental aspect of these dualities. And looking at it, in particular in the free models, one realizes that this is typically a category of opponent starting games, and this is a category of player starting games. So maybe there is, you know, again, this vision that logic is symmetric, okay? There is a player and there is an opponent. They should kind of, and in a way here, it's a biased view, because we give dominance to C over CR. unfair. Why should we say C? And you know, it's like, I'm not C up. You know, I'm not your opponent, I'm me. You know, so let's try to have an unbiased view. So this gives a slightly bizarre idea where we take a category and we decorrelate it from C up. Okay. And my claim, if you like, is that linear logic is confused because in that case C is equivalent to C up and you don't see the partners in the game. Okay. So here we have A and now B. A is equivalent to C and B is equivalent to C up, and we try to understand how we can formalize the data we have. So let's take a dialogue category formulated as what I call a chirality because it has to do with two people. Well, what you get is, of course, a monoidal category for A and a monoidal category for B. But the tensor is called AND here and the tensor is called OR here. Okay. Now, of course, you're not stupid, so you remember that B side is the same as A up. So there should be a monoidal equivalence between A and B up. Okay? So 0, 1 means it's opt as a category, but also opt as a monoidal category. So you turn the tensor upside, inverse the orientation of the tensor. So A, of course, is like B up. Moreover, there is this adjunction between C and C up. So we keep the adjunction here. And then something which is nice is that we see a bracket coming in. The bracket is defined like this. You remember here we have A up and B. Okay? So we can define, this is exactly, this bracket says I pick a formula here of the player and the formula of the opponent, and I get a set which is just C. Okay, let's see whether it works. It's C of A not B. Okay, which is in a way is something like C A tensor B to the bottom. Okay. So that's the bracket, and we see that this will play the role of the form and the Frobenius algebra. So every Frobenius algebra is a monoid with an associative form, and this will be exactly because you see this is associative if you think in this way. So okay, I'll come back to that a bit later. But okay, and then we have coherence diagrams we speak about. This is curification here. Okay. So curification, what it says is if I have a map from M tensor A into negation of B, I can transport M here. Okay. And if I have, because I have a left purification and a right purification. And that's it. Okay? So you see, these things are quite neat, and what is nice is that we can speak about these things in a situation where negation is not involutive. Okay, so it looks like we are doing something like linear logic, but in fact we don't need an involutive negation to do that. Okay, so let me say that we have three coherence diagrams, which are very basic. Typically, if I clarify M in one step, it's like clarifying first M and then M. So now, what we've done is we took a dialogue category and we gave some kind of fair account of it, where we have C and C up treated fairly. How much time do I have?
5, 6.
Okay, that's okay. So let's try to do the same with Frobenius algebras. So you see, it's very symmetric too. So there is a temptation to say, maybe here I have a bit of C and C up again, okay? And really, you know, I'm sure I would have been, this really is a development of day and stream. Okay? What I simply do is take a nice observation and a nice theorem in the linear logic and lifting it to see what I get as, what kind of lax notion of Frobenius algebra I get. So I will explain how it works. So in the case of Frobenius monoid, we know that F is isomorphic to its dual. Okay? And there is a form here which is associative. So associativity means x times y compared to z is the same as x compared to y times z. Okay? And this is, you see, it looks a bit like these things here. So let's try to develop that. Okay, so And again, as in logic, there is a perfect symmetry, if you like, between the monoid and the comonoid. So we can say the monoid speaks to the comonoid, who speaks to the monoid, who speaks. Okay. And so let's try to take a fair account, unbiased account of that. So we have a monoid in blue and a comonoid in red, and let's see how they should interact. And really what you need is that there is a duality, okay, a dual pair, between A and B. Because remember, A stands for the Frobenius algebra, B stands for its opposite, if you like, and then we need to relate them by a kind of self-duality here, which says that if you wish, B is a dual of A. And so this is what you get pictorially, and what we ask also is that, of course, the co-multiplication is obtained from the multiplication and the duality. Okay, so they live well together. And here, when we look at this thing, it reminds the notion of chirality. And we see that indeed this is the case. So if you like, this kind of two-sided formulation of Frobenius algebras is, is hidden some logical structure. So let's try and understand what is the logical structure. So, the first thing to say is that the Frobenius monoid can be seen as such a pair where A and B are related by an isomorphism. Okay? So this means that, if you like, we have A, we have its opposite, which is B, and moreover, we ask that A is equivalent to B by this, or isomorphic to B. Okay? Which is the same as in linear logic, we have C and C up, and they are isomorphic. So the idea would be, yes. So the idea really would be to replace this isomorphism by an adjunction. But in order to do that, we need to shift from monoidal categories, which is the place where typically this notion of Frobenius algebras live, to monoidal bicategories. So that's fine, but then the problem is that, for instance, if you work in cat, well, B here is supposed to be A up, but it's not dual to the category A. Okay? So here, in the case of Frobenius algebra, B is a dual, algebraic dual to A, but here it's just the opposite category. But then, the idea is that, so this is, like there is a little miracle, okay, is that if we move from from categories and functors to categories and bimodules between functors, okay, or distributors, then we'll have really something wonderful happening, which is that C up is dual to C. So if you like, we live between categories and functors, well, that's the place where we stand usually, but when we embed this universe into a larger universe where we have categories and bimodules, it's well known, and this is the typically, so there is Benabou here, and there is the Australian school, that in fact suddenly C up is a dual to C in that universe. So then, maybe if we are sufficiently precise, we can reformulate the notion of dialogue category in that language, taking advantage of the fact that there is C up in the definition of a dialogue category, and which means a dual, just like in the case of Frobenius algebras. And so this duality is expressed as something which is a refinement of duality, in the sense that you have, instead of equality here, you have some two cells which are invertible, and so you have some coherence diagrams which are formulated like this. But the important point is we can reformulate the notion of chirality in that language, so in that bialgebraic language. So what is a chirality? I call amphimonoid, yes? So it's a pseudo-monoid, a pseudo-comonoid, which is if you like, something like the opposite category, and then some pairing between them. Okay. And this is exactly saying I have in the universe of categories, I have a category, its opposite category. And the fact that B is the opposite category is described here. Moreover, I ask that the fact that B is equal to A up, I ask that this equality or this isomorphism reflects the tensor product. Okay, so fine. And so when I'm here, I'm happy in a way, I kind of describe my chiralities, and I want to have dialogue categories or dialogue chiralities. So I will add some adjunction here, and the adjunction here is organized in this way. So you see, it's just a refinement of what we had for Frobenius algebras. So this is the equality I need for Frobenius algebras. So for this lax notion of Frobenius algebra, I have the same, except that now these are isomorphisms. And the point is that these isomorphisms are able to curify in the language of Frobenius algebras. 1 minute. So, okay, so you get some coherence diagrams too. And the theorem, okay, looks really a bit frightening. I mean, if you're not used to these things, but it's really in the style of Day and Street, if you like. So what this says is that a helical dialogue chirality, so this notion, this logical notion, is the same thing as this Frobenius amphimonoid, so which is like a Frobenius algebra, but in a lax sense, in this bicategory. And what you ask is simply that these 4 bimodules here are produced by functors. So that means here, this is the negation, and the left negation, the right negation. This is the star from A to B up, and this is the map from B to A up. Okay, that's fine, but the new thing, and okay, I will just take just this slide, okay, which I produced in the corridor. That's what. So that's okay. So this is just a drawing which shows that we can do proofs, we can understand proofs as transformations of these cobordism diagrams. So here what I've depicted is how you do the strengths of double negation. So this is double negation, this is double negation of A1 tensor A2, and here by transforming it I get A1 tensor, so I have a big pen, I should write what I need here. Okay, so what I wrote here is A1 tensor double negation of A2 is mapped into double negation of A1 tensor A2. Okay? And this thing in game semantics is the most basic building block of innocent strategies. Okay? So if you can build this map, you can build any innocent strategy between games. So what I claim, if you like, is that innocent strategies can be seen as the flow of the negation functors here in this kind of diagrams. Okay, so here you have R, which goes here, and so on. And that gives another geometric point of view of what is a proof. It's a flow of information in this kind of cobordism. Geometry. That's it. Sorry?
You have time for some questions.
Yes.
Yeah.
Can you go one slide back? I didn't understand the pictures there.
Which one?
Because you got the red going into blue.
This one?
Yeah, but the red goes into blue on the 2 right-hand side pictures. What is the piece of red?
So red means B.
Yeah, I understand, but like the way you sort of cut them up.
No, the thing is that I describe. Yes. So home is, so this is B here, and here I will move to A up. I will move to A because this is the connection between B and A, and now here I will move to A up because remember that this picture lives in bimodules. So A is dual to A up. So this is the duality. So if you like, what happens is we need to understand how the kind of canonical duality of categories here interacts with something which has to do with the fact that we have 2 sides in the dialogue. So you know, after I think Jamie gave this talk, I said we don't really understand how logical dualities and geometric dualities interact. Okay, and here it's a typical example because the blue and the red correspond to the 2 partners in the interaction, and then there are phenomena which comes from the geometry, and we need to understand them properly to this shows, okay, maybe something, it's that we can do proof theory inside an appropriate notion of Frobenius algebra. Okay? So every proof in this more language of tensorial logic can be done. Maybe I should mention that. In order to do that, I need some dagger structure on the Frobenius structure. So I need that. Okay. I need some adjunctions. So this means that we can kind of understand better what it is to build a proof.
Can I ask a little clarification? You have two linear implication and one negation, if I understand.
Here I have two negations,
Two
the left and the right.
And two linear implications too.
In fact, because linear implication is very difficult to understand in this diagram because we don't have a good coherence theorem for monoidal closed.
The sequence calculus.
So that's the reason why I moved to negation, pure negation, because there we can have a coherence theorem like the one, so we can characterize the proofs as some kind of.
So two negation and the tensor.
That's it. Yes.
Okay. Like in pregroups and stuff. Well, not exactly the same probably. Perfect.
Okay, we start in half an hour.
So many things are going in the direction of
Are you going to come?
Sort of, yeah, because
I can take it from now.
yeah, okay, great. It's really simple, and actually I've been